They are recording these. I don't know, no, I don't see any. There is a camera back there, so I don't know if Dan's going to have these things available after the fact, but if you check out my YouTube channel, you can see me. Got me covered. That's all that counts this week, right? All right, how many of you were in 70B this morning? Awesome. Awesome. How are you going to be? How many of you are going to be in 70B tomorrow? Okay. Beautiful. All right, at least I got some of those covered. And we are streaming, and you know, by now you have already been through the PDH routine. My time checker is right here. He's on the job. It's 1 o'clock. And you're going to tell me about quarter till. All right, all right. Yep. I usually set an alarm on my phone, but my phone is right there now. Okay, so, but I do have my iPad, so I don't have an excuse. I have my scepter. This thing is powerful. Take down a single plane with one. It's wicked. The green is better than the red, just to tell you if you're ever looking for a pointer. Okay. We're going to get started. We're going to talk incident energy and the National Electrical Code. Well, we're going to explore a little bit about incident energy as we go through. There are relationships between the two. We'll relate it to the National Electrical Code. We'll talk code. My name is Thomas Dimitrovich. I sit on code panels 2 and 10 for the National Electrical Code. Panel 2 handles Article 210 and 220 load calculations. Panel 10 has Article 215 for feeders, 225 for outside branch circuits and feeders, 230 for services, 240 for overcurrent protection devices, 242 for surge. And I believe there's a 235 in there because we separated this cycle. We moved medium voltage into its own articles. A lot going on in medium voltage and the NEC, so keep your eyes open for that if you're into medium voltage. So I sit on the code panels, but I do not speak on behalf of anybody on a code panel. I don't speak on behalf of NFPA. I don't speak on behalf of Eaton or anybody else. What comes out here started up there, and I try to share what I know. So, and hopefully we'll have a great discussion today. All right? Believe half of what you see and less of what you hear. Ask questions, please. So, can someone tell me, what was the first year an arc flash reduction technology went into the National Electrical Code? Let's talk decades first. Was it the 2000s, 90s, 80s, 70s, 60s? 2000s? 90s? What if 70s. Who said 70s? Okay, we got a couple. What's, you guys are in the right ballpark. You're in the right decade. You got it. Now, there might have been a guess, but I'm going to go with, you guys know exactly what you're talking about, because you were going to say 1971 code had the very first technology in the National Electrical Code to address incident energy. What do you think it was? I'll give you the first two words: ground fault. For circuit interrupters, GFCIs are for shock protection, but ground fault protection of equipment. When in 1971, because three things occurred up until that point. What types of systems, most industrials, did they have? Grounded or ungrounded? Ungrounded, and then they moved to what? Grounded. So what happens? When you're an ungrounded system, you're a boat afloat in the ocean going with the waves. Your voltages are going up and down and all this jazz. The first fault is a gimme, right? You have to have the little indicators and you try to walk around the plants, and we have great methods to help identify and locate ground faults in high impedance grounded systems and all that jazz. But then someone said, boy, there's this guy down the ways who has a ground fault all the time, and he doesn't have the loss of all the voltage issues, of all the transient events that are going on in the facility. He doesn't have as much equipment damage. We sort of like those grounded systems. But then they realized that once you ground that system and you have a grounded system, that first fault is no longer a gimme, it's a doozy, right? So the second thing they did, the systems back in the day were 208 volts. That's what they were. They pumped it up to 480. Now, what's voltage in a power distribution system? Pressure. So now you had a grounded system, you have higher voltages, and the average service size went from a 600 amp service to upwards of 4,000 amp services. And what happens if I'm a time current characteristic curve, which we're going to look at? So 0, current, I'm the instantaneous on a 600 amp breaker. When I put in a 4,000 amp breaker, I go this way in my instantaneous. My instantaneous pickup goes larger. So what the industry started to experience when they made those 3 critical changes was burn downs, they called them, of service entrance equipment. Arc flash events on service entrance equipment. And the solution back in the 60s, moving into the 70s, is when we started to get computers that went from the size of this room down to integrated circuits. We were able to put them in relays, and we made the ground fault protection of equipment with sensors. And that was to address, it went in the 1971 code, and if you look at the public inputs and the substantiations, they had an IEEE papers that were going on at the time. They were showing all of the damaged equipment and service entrance equipment, and that's what ground fault protection of equipment was meant to do, was to protect service entrance equipment from arc flash events. So that was the very first one that went into the code. Today, and since then, it wasn't until 2002 that we had some marking requirements around incident energy. And it's very important to turn the button from red to green so that you can advance your slides. All right? So, you guys and gals know this is an RCEP continuing educational program for those of you in the room, not for those out on YouTube or Facebook or LinkedIn or et cetera, et cetera. And the educational activity is protected, blah, 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 good stuff. Arc flash. An arc flash is the light, heat, sound. So if you think about an arc flash event, unfortunately, whenever we talk 70E, everybody wants to talk about arc flash. Why? Because we have the rubberneck syndrome, right? We want to all watch the big lights go off and all the events. More people die from shock. More people die from shock. But arc flash, and we have shock protection in the National Electrical Code. We have barrier requirements, all that other great stuff. So I do want to say, although we're going to talk about incident energy, shock is the #1 killer out there for us. But when an arc flash event goes off, you have light, heat, sound. You've got shrapnel. You've got pressure. We have IEEE 1584 that helps us calculate energy heat only. IEEE 1584 doesn't tell you what the sound is going to be, doesn't tell you what the pressure will be, doesn't tell you how much shrapnel is going to come off of the equipment and subject the electrical worker to that violent event. But we can calculate the calories per centimeter squared, the heat only, although there are a lot of other components that are a part of an arc flash event that we just we have personal protective equipment. We still have to have our ear protection. The shields and whatnot are tinted so that we can protect our eyes from the ultraviolet. It's like watching an arc welding, right? You don't want to watch a weld go on without protection. Now what happens though, you have to initiate an arc flash event. Now we're going to talk about risk. And for those of you who are in the 70B class this morning, I don't want you to answer the question. What are the 2 components of risk? Likelihood and severity. Absolutely. Everybody in the first class, everybody said severity. I was like, that was beautiful. Likelihood and severity. So when you think about an arc flash event, what I'm showing you here is what? Is it severity or likelihood? It's all severity. Likelihood is up to us. It's up to, you can't plan or predict what's going to happen on a job site. So we have code requirements that address both of those buckets. And I'll tell you what I did for 1 week. And I didn't tell my wife because she would have thought I was crazy. But I looked at everything I did with regard to likelihood and severity. You get into a car, you're accepting some level of risk, right? When you're in your car, you may have your seatbelt on and you're driving down the road doing 50 miles an hour, and what happens? The phone rings. Now, you do a risk assessment at that point. Do I look at the phone and see if it was my boss? Do I maybe hit the dash and see what's going on? Do I actually pick it up and send a little text? All of that is a risk assessment. And everything you do from the moment that phone rings is you accepting some level of risk. And we all have a personal level of risk. Anybody ride a motorcycle? How many bike riders in here? Do you wear helmets? Absolutely. Do you wear leathers all the time? Man. See, I can honestly say I wear my helmet all the time. And I'll wear my jacket because it's cool. But sometimes I'll wear shorts. I really do. And it's stupid, right? And you see a guy going down with his boots and his shorts on. But we all accept some level of risk in everything that we do, but the challenge is not to accept it on a job site. Because my risk, when this goes off, my risk that I accept impacts everybody around me in that room. So this is all severity related. This parts of the puzzle. So you have IEEE 1584 is what we use to calculate incident energy. And it recently went through a change. And 2002 was the first edition. 2018 is the second edition. You have 70E, which is our de facto industry, I guess you'd call it, our reference for the industry on safe work practices. And they give you two methods in there to determine and labeling of equipment. They have the PPE category method, and they have the calculating of incident energy. Both of those are valid. I will give you some of my opinions. If you don't know me, you'll know me. I'll give you my opinion, right? We all have opinions, but I'm up here, so I can share mine. And if you have an opinion, please, if you have questions, shoot them out. Because that's all we can calculate. So when you look at IEEE 1584 and how we did the testing, we did a box, and here's another argument that I think is very valid and fair, which when we went from the 2002 version to 2018, there was a lot of controversy. There were a lot of people that said we shouldn't spend the money in doing the additional testing because there isn't anybody who dressed to 2002 and came out underdressed. Right? So then we put all this money in to calculate incident energy, and we made changes to the equations to account for the size of the enclosure. Smaller enclosures push more energy out the front. Larger enclosures don't focus as much energy. Whether the bars are this way or this way makes a difference. Whether they're this close together or this close together make a difference. There's a lot of parameters that the additional testing that was done to publish 2018 that gave us more insight. And it changed two critical things. One was the incident energy calculation, but the other is the arcing current itself. Arcing currents went up for the most part in all of our calculations when we came out with the 2018, and that's not a bad thing. It's actually a good thing. There's a big misconception. I was working with an engineer one time. He says, he goes, I have a problem with a drawing. He had a drawing, he has a customer, and his customer wanted so many calories per centimeter squared. You know, he had a design for like, it was like 6 cals or 4 cals and then 40 or whatever, and he wanted to get it down below the 4 or 6. And he said, I don't know how to fix this. And his arcing currents were low. They were in the long clearing time, and he had high incident energy. So we were going through it, and I you know, it's like one of those things where you go home and then you go, oh, I know exactly what to do. So I shortened up the run, and I put parallel conductors in parallel to increase the short circuit current, and it increased the arcing current, and his energy went through the floor. So I called him up and I said, hey, you need more fault current. He goes, hey, you're crazy. I said, no, you need more fault current because let the device do the work. So when Dr. Lee did the testing down in St. Louis, He creates, we call it arcs in a box, basically a big square box where we have our electrodes, we initiate the fault, not a piece of equipment. And we run, he did test after test after test, and then he changed the size of the enclosure, test after test, and then changed the configuration of the electrodes. And all we do is we put sensors out in front to measure the heat. We don't have pressure indicators and all that jazz to measure how much force or how much shrapnel. Can't measure how much shrapnel because I'm not testing in equipment. And the argument from many manufacturers is that, well, when you have that same arc flash event in equipment, you're not going to have the same results. It's probably going to be a lot less because of the spacing and everything else. But we can't get the testing in everybody's equipment because it would just be way too expensive, right? So, because there's so many configurations. So 1584 went through that whole process, and we calculate the calories per centimeter squared, and we wear our PPE to meet the calories per centimeter squared, but that has nothing to do with the force and the shrapnel, and I might break my ribs. Fall protection. I have fall protection, right? You say you put your fall protection on, it's the last resort. Hopefully you don't have to use your fall protection, but that doesn't mean if you do use your fall protection, fall off a scaffolding, that you're not going to get killed. Okay? Race car drivers do the same thing. They get in a car, they wear all their equipment, and you would think, well, hey, after an accident, they're okay, and boom, they die, right? So PPE is your last resort, and that's unfortunate, but that's all we can do. But we do manage risk. 70 helps us manage risk. We're going to talk about the different areas of National Electrical Code that help us manage either likelihood or severity. So 70E is our standard for the workplace. 70, the National Electrical Code, we're going to talk about that. 70B is maintenance, and that was the discussion this morning, and they're all very interrelated. 70, 70B, 70E, I call it the trilogy. They are very closely related, but 70E and 70B give you the recipe on how to create your either a safety plan or your maintenance plan. The National Electrical Code is what I'm installing, and it's there at the time I'm installing. OSHA. OSHA is the enforcement arm for 70E, right? Because I don't have an AHJ walking through my facility and inspecting to 70E. They'll inspect to the National Electrical Code, and if the National Electrical Code says you have to have ground fault circuit interrupters, if they tell you you have to have barriers to reduce likelihood of accidentally coming in contact with something, if they tell you you need working space, they can tell you all of the things around the installation, but they're not going to enforce your safety plan. Unfortunately, some of us will experience that through the OSHA investigations after an event, but it's up to us to police it ourselves. And then, so you have 1910, which is your health and standards, and then safety health regulations for construction is 1926. And honestly, if you look at like lockout tagout, one of those is really bad in lockout tagout. I mean, you could probably use this paper clip and say it meets the requirements of OSHA's lockout tagout rules for one of them. And I can't remember if it was 1910 was the one and 1926 was better. I can't remember, but in any case, OSHA is your link for safe work practices. Now, 1584, you'll see the addition on this is 2018. There were a lot of studies that were done. Dr. Lee, again, over and over and over, but it's arcs in a box. You have vertical bus, VCB, like a panel board would be a VCB configuration. You have VCBB, that's a vertical bus with a barrier, an insulated barrier. That's the end of the bus is close to a barrier, which it could be that on the secondary of a circuit breaker, close to the end rails, but it has to be insulated, an insulated barrier. You have HCB, which is a horizontal, which is what you might see in a motor control center, low voltage assemblies, things of that nature. And what that means is that you're staring at the end of the bus. And how I relate that is, remember, the arc flows away from the source. So if you're in a VCB vertical, you're like standing. You're in New York City, in a subway, standing on the edge of the train track, watching the train come past you. And then you'll feel the air come at you. That's a VCB. The arc is flowing down and then it bellows out. HCB. you're looking right at the train. You're standing on the tracks and you see the light coming and it's right there, it's going to hit you. So HCB is always going to be the worst case scenario. Now the challenge in low voltage assemblies and motor control centers is, where is your electrical worker going to enter the equipment? Are they going to be seeing a VCB configuration or an HCB configuration? And that is the dilemma that we as engineers face as we calculate incident energy. And most of us in those larger assemblies are going to probably err on the side of caution, because that's what we engineers do, and mark the HCB configuration, because you don't know where they're going to mark. And you can't say, well, this cubicle I'm going to put an HCB, and then over here I'm going to put a VCB. You just find the worst case for that assembly and you hope that they're dressed for success. So this document, a lot of research went into play. The first edition was 2002, the second edition was 2018. Took us 16 years to come up with the second edition. Two things you need. Outside of the size of the enclosure and all this other good stuff, you need current and you need time. And what determines how much energy I let through is the protecting overcurrent protective device. Now, if I'm working on this piece of equipment, let's say that this is a panel board and it has a main breaker. And I'm going to turn the main breaker off. I'm going to lock and tag that main breaker off. And I'm going to take breakers out on the load side of that main breaker, and I'm going to work in this panel board. Do I rely, is that establishing an electrically safe work condition? Is there an incident energy? Is there a likelihood involved with an arc flash event that could occur even though I turn the main breaker off? Right. So I could accidentally, now what do we do in the code to reduce the likelihood of that for service entrance equipment only right now for 2020 code? I put barriers to Article 230. And we put barriers in the 2017 code in Article 408 for panel boards and switchgear. And we added panel boards in the line side barrier requirements for service entrance equipment. And we moved it to Article 230 and we said any service entrance equipment, we want barriers, but you can't rely on the barriers for calculating incident energy. You always have to go to the supplying overcurrent protective device. So if this is a panel board and I turn off the main, I can do all that jazz. I still have incident energy that is, I have potential here, but it's based upon whatever breaker is feeding it from the upstream overcurrent device. And I call that the protecting device. Because this device, which feeds that piece of equipment, is what's going to determine the incident energy here. And if I accidentally touch the line side, or if I'm doing justified energized work, and I have an arc flash event where I have, remember the plasma, right? Where is it? A highly conductive plasma. So I'll have a plasma, I now call it the plasma cloud because people laughed at me when I called it the plasma plume. So it's a plasma cloud that occurs. Once you initiate an event, you'll get a highly conductive area that can propagate to the line side. So 1584, and I believe it is 1584.1, will tell you you need to consider a line side propagation or accidentally touching the line side conductors. And then the clearing time, which is determined by the resume of an overcurrent protective device, which is the time current characteristic curve, that's going to tell you how much time it's going to take for that arcing current to clear. So your incident energy in this piece of equipment is going to be based on an upstream overcurrent protective device, which is going to be determined by how much time it takes for you to clear the arcing fault, which is the first challenge of the PPE category method. The PPE category method, how many of you are familiar with the PPE category method in 70E? So with the source of the PPE category method has, I think, very valid roots in that many electrical workers who work in a non-labeled environment need a way to determine what level of PPE to get into. And so the category method is a method for them to get that done. And it works off of the three-phase voltage fault current value not exceeding a certain number. So for panel boards, I believe it's 25,000 amps. Anything above 25,000 amps, you need to have a calculation done. But if it's below 25,000 amps, then you can use the PPE category method. But what did we say? Not the high fault currents that get you, the low fault currents, right? The lower the fault current is, the more chances I'm in this long time region from a clearing time perspective. My instant energy goes up. You want to feed the beast. More current, faster clearing time. My dad used to tell me when I was a kid, I used to work my butt off. He'd say, let the tools do the job. This is your tool. Feed the beast. Give it enough current and it will act appropriately. And the fuse, same way. And in fact, you don't want to be in this side of the fuse, right? So it's the lower currents on the fuses and they have a much higher, faster rate of rise. This is like falling off a steep roof as opposed to a flat roof. I'd rather fall off a flat roof. So, and that's your flat roof. But you want to be in the current limiting region of a fuse. You can't get anything that will work faster and more efficient than that overcurrent device. So now what I did was, I took a 600 amp circuit breaker and I used now, there are three types of circuit breakers. Molded case circuit breaker, insulated case circuit breaker, and a power circuit breaker. I can buy a 600 amp circuit breaker in all three of those. Why? Power breaker, 600 amp power breaker, I'd need a truck, little cart to get it in here, right? And it's gonna go in a big gray box. I could buy an insulated case that'll go into a smaller gray box, but I'd probably say, maybe on one of my good days, I could probably carry an insulated case circuit breaker, not a double wide, forget that. But then you get the nice little multi-case circuit breaker. Why would I buy a 600 amp power circuit breaker? Anybody know? You want those contacts to stay closed as long as you can for upwards of 30 cycles, up to the interrupting rating of the circuit breaker. So there's effectively no instantaneous, okay? Why would I want that? Is because I want all my little puppies downstream to clear the faults, so I'm not taking the main out every single time there's a fault downstream. I want those contacts. What do you think is harder for a circuit breaker? To open during a fault or keep the contacts closed during a fault? Keep the contacts closed, because I can't have this. It's called chatter. We can chatter. We don't like to chatter when there's class going on, but when we're out there, you hear all that chatter, but you don't want contacts, because if they do this, they get dimples. They look cute on us, but not on the contacts of a circuit breaker. They generate heat, and then boom, you get failure, right? So we want that thing to open. And it's easy for it to open because we rely on the magnetic forces. We will arrange the bus bar so that the magnetic forces push them apart. And then for me to hold it together for 30 cycles, I need to bring Lou Ferrigno to the job, okay? Or Arnold, and hold this. So what I need bigger, beefy meat. I need more springs. The device gets bigger. The infrastructure gets bigger. So what I always tell apprentices, when you go, if you're in a power distribution system and you see little equipment, good. Big equipment, bad. Because the closer you are to the utility, the larger the equipment gets, for the most part. So, larger circuit breakers, I can buy a 600 amp breaker in the power breaker, 600 amp in the molded case, and everything in between. And the reason I would pick one over the other is because I intentionally want those contacts to be held close for a longer period of time. I'm going to have higher incident energy downstream of the big boys. Right? So, this is a molded case circuit breaker. I set my software up to be the exact same configuration for each circuit breaker. So I didn't change anything. It's the same voltage fault current value, same, the enclosure size is different. I did change the enclosure size. I think I did. can't remember right now. But in any case, everything is the same except the clearing time. 25,900 amps is in, it's not quite the current limiting. How do I know if I'm in the current limiting region on a TCC curve? Has anybody, do you guys know what this is? You know how to read a TCC curve? Higher the current, that's the clearing time. How I know, what is, when I say current limiting, what do I mean by current limiting? What's the clearing time I can expect? What's one cycle? How many seconds is one cycle? 60, 1 over 60. 0.016 seconds, give or take. 0.016. Half of a cycle is 0.008. 1/4 of a cycle is 0.004. This starts at 0.01. So if this is 0.01 and that's 0.02, one cycle is 0.016. So one cycle is about right here on this curve. Half of a cycle is 0.008, so it's below this curve. So current limiting devices will clear within a half cycle, right? And if it's a current limiting fuse, it's going to clear within a quarter cycle. They give a little bit more because you have, from a breaker perspective, we got a lot more stuff going on, right? Fuse is just an element that's melting and gone. So fuses are held to a little bit higher standard when it comes to current limitation, but they'll clear within 0.004 seconds. So I'm not quite in the current limiting region. I'm at 0.012 seconds on this, and I've got 2 arcing currents. So 1584 has me calculate 2 arcing currents. Very important, especially when you're going to apply 24087 and 24067, because both of those code sections are very vague in this regard. I will calculate a higher arcing current and a lower arcing current. Anybody know why? Dr. Lee. Dr. Lee. Great guy. But who in here liked their professors in college? Okay. Oh man, there's a couple of you. You both lie. Anyway. So what Dr. Lee did was he says, look, I'm going to do these arcs over and over and over and over and over. And then he has for a bolted fault, say a bolted fault value, and this is an arcing fault value. He also, for a specific bolted available fault current, he gets a data point. Then he does it again, he gets a data point, does it again, he gets a data point, does it again, does it again. And if there's anything you know about arcs, they're like snowflakes. No two are the same. So then he says, I'm going to increase the bolted fault current value, and then he gets here, 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 and here, and he does the same thing here, 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 and here, 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 and he does all these data points. Then, like engineers do, we draw a line up here, and we draw a line down there. The 2002 edition, he didn't draw the second line. He just did a percentage. Remember, the 2002 just did a percentage of the one arcing current to get the lower. In the 2018, he actually drew the curve and he came up with a different equation for the minimum arcing current to make sure that he encompassed all of the arcing currents. So we have 2 different equations, and again, this is just a 2-dimensional. You got to add the 3rd dimension, which is the configuration, the spacing, everything else. So very complicated math. And then we use these equations to calculate the maximum and the minimum arcing currents. And then we compare those both with the clearing time. I can have a minimum arcing current that takes a longer time to clear, which will give me my maximum. Or if I'm in, say, this region right here, and they have both arcing currents have exactly the same clearing time, the maximum arcing current is going to give me my maximum incident energy. Okay? So, when they both have the same time. So, that's why you're seeing both of these. Now, 24087 and 24067 has us do a comparison with arcing current, but it doesn't say whether you're doing the maximum or the minimum. As engineers, in my opinion, my humble opinion, I would say the minimum would be your worst case, because what you're looking at in 24087 and 24067 is whether or not you are operating the arc reduction maintenance switch or operating instantaneous or any of the technologies that are recognized in 24087 and 24067. Your lower arcing current is going to be your worst case. But the code is vague on that. Very vague on that. It doesn't say. So in this case here, for this molded case circuit breaker, 600 amps, I have 0.01 seconds, 0.012, 0.64 calories as my worst case. Now, all I'm going to do is change the breaker to an insulated case. Now, insulated case is really a molded case circuit breaker. Insulated case circuit breakers is a marketing term. It has nothing to do with codes and standards or engineering, period. It is a marketing term that the industry recognizes. Just like I fight this with my resi people. They'll say, I have a load center. I'll say, okay, well, you got to go to UL 67 for panel boards. No, it's not a panel board, it's a load center. Marketing term. Okay, insulated case circuit breaker, UL 489 device. Molded case circuit breaker. Now, for the same two fault currents, arcing currents, I'm in a 0.15. Now, obviously, I set the short time. So let's talk about the curve. Long time pickup. What do we use that for? That's your overload. What's it there to protect? Your equipment and your conductors, right? You don't move this puppy, because if you move it to the right, you can no longer protect your conductor or your equipment ratings, right? Because that's your overload, that's your persistent current pickup values. There's your short time delay. Why would we adjust long time delay? That's a long time delay. Anytime I say delay, it's time. Pickup is current. Why would I adjust the long time delay? Motor startup, transformer, I don't know about transformer inrush. Motor startups or selective coordination, right? So short time pickup, I can move that left and right. The only reason I would do that is for motor starting possibly, transformer inrush possibly, selective coordination, or if I want to use it for some arc flash reduction to give me this knee, take a knee, reduce incident energy, get it to a reasonable value, better than going up to this portion. So I might do that. And then I have the instantaneous pickup, which I can move around, typically for selective coordination, motor inrush, transformer inrush, etc., etc. Same scenario, I'm at 12.7 calories per centimeter squared. Oh man. All right, 30 cycles. This is a power circuit breaker. 30 cycles, I'm at 31.8 calories per centimeter squared. And all I did was change the power circuit breaker. That's a different standard than 489. All right, the magnitude of incident energy depends on the current that will flow, etc. Already said that. We know risk. Installation requirements will help us address likelihood and severity. If I look at the NEC for the areas that are, I call it the direct NEC requirements. I've got 110.16, which is labeling. 110.16b had a journey. We put the guy who just says, danger, we put him in 2002. Why did we put him in 2002? Because 1584 was first introduced in 2002, and then there were people who were on the IEEE committee who said, hey, we should have labeling everywhere. We should use this document. So they put public inputs in to label all panel boards, switchboards, and switchgear with an arc flash label, and they didn't get what they wanted. All they got was accident guy, right? Saying, hey, this is a hazard. Only if you're going to do justified energized work, right? So you got to read the details. Devil's in the details. So you have 110.16, and then in the 2023 cycle, we changed the labeling. Remember, in the 2020 code, or the 17 code, I think it was the 17, they put the labeling for 110.16b. In 110.16b, they said you need to put the voltage, the available fault current, the clearing time of the overcurrent protective devices, and what else? There was a third one. Voltage, current, I think clearing time, those three, and the date. 70E does not require a date on their label, but the National Electrical Code requires a date that you made the label. So 110.16b was introduced, I believe it was the 17, and in the 2023, they removed the available fault current. They removed all of those requirements for marking because it can be hazardous. If I'm using the PPE category method and I use those parameters to determine my personal protective equipment and I'm in service entrance equipment, what's the incident energy dependent upon in service entrance equipment? Is it dependent upon the main service overcurrent protective device? Right, the fuse on the primary of the transformer, which is not there for anything on the secondary. How do I pick the primary transformer overcurrent device? I pick it a little bit bigger, right? Because I gotta work through inrush currents, and it's usually like 1.5 or 1.25 or maybe 1.5, maybe up to 2.5, because I might have to do some selective coordination through a transformer. So 110.16b was a marking, and then 240.67 and 87 came on, and that was to address incident energy, specifically because of the incident energy discussions around selective coordination. I was going across the country telling people, hey, look, if you're going to selectively coordinate, you got an issue with incident energy, because if your short circuit value of bolted fault is not in the instantaneous region of the upstream device, where's your arcing current? Down in that lower long time clearing. So a friend of mine, Jim Dollard from Local 98 in Philadelphia, he put together the language for 240.87, and then 240.67 came into play. 110.16b was just expanded for feeder supplied equipment. From 1200 amps, we moved it down to 1000. So any equipment 1000 amps and above is going to need an arc flash label based upon NFPA 70E. Or, I mean, 70E is like the de facto. You can't write that into the code, but we reference it. This is sort of what it says, and feeder supplied equipment, arc flash and feeder supplied equipment rated 1000 amps or more. The arc flash label shall be in accordance with acceptable industry practice, and then the informational note points us to 70E. So the 2023 code expanded that down to 1000 amps instead of 1200, and we hit feeder supplied equipment. All right, 240.67, you have where fuses rated 1200 amps or higher are installed. A and B shall apply. You have documentation, you have a method, and you have performance testing. 240.87 is the same way. You got your documentation, you have the methods you can use, and you have your performance testing. Now, the challenge with especially fuses. We probably didn't buy a fuse because there was only 20,000 amps available fault current at the service. You probably bought it because there's over 100,000 amps available fault current at the service. IEEE 1584 only applies up to 106,000 right there. Up to 106,000 of bolted fault current value. If you have more than 106,000 amps, you can't use 1584 to calculate arcing current. There is no method to calculate arcing current above 106,000 amps. If I have 150,000 amps and the code says you have to be within a 0.1 second clearing time on your fuse, and you have 150,000 amps at the arcing current, you can't calculate arcing current. How the heck are you going to meet 240.67 and 240.87 if you have fault currents above that? So I came up with a little technique, but in any case, if you look at like this table here, I'm going to walk through it. If I have a 4,000 amp fuse, I'm right here. My 4,000 amp fuse, and if I have 150,000 amps, I have no way of determining my arcing currents. So my suggestion is to calculate it at 106,000 amps and compare your arcing current of 37,006 with the instant or the clearing time of the fuse, and determine whether or not it's 0.1 seconds or not, which is the requirement on the code. 0.01 second, 0.1. How good am I? I got 8 minutes. All right. Columbus sailed the ocean blue. So the other thing you can do is split that into two 2,000 amp services. Now you're in here, and as long as your fault current is greater than 24,000 amps, you'll meet the requirements of the code. You'll be in the 0.1 second clearing time, and you don't need an arc reduction technology because your fault current is high enough. Same thing for breakers, right? If you compare the time current characteristic curves, and if you look at, you can use the instantaneous on a circuit breaker. You can use the current limiting nature or 0.1 seconds clearing time for the fuses. You just have to do the comparison of the arcing current, and I would suggest the lowest arcing current. The code doesn't say lowest arcing current, it just says arcing current. And arcing current's not defined. So I gave you a series of fuses. You got your fuse amp ratings, got your bolted fault current values. There's your arcing, that's your minimum arcing fault current. There's your clearing time in seconds. Now, I have the Lee method. Honestly, as I got into this, I do not like the Lee method. It's recognized by 70E. The Lee method does not use the arcing current. They use the bolted fault current value to determine clearing time. And we as engineers know you can't do that. So it may be tempted to say, oh, I just did the Lee method. So if I looked at, like I look at this analysis, I took an analysis that, I took an analysis, I took like a 3,500 or a 3,000 amp fuse, and I did it at 106,000 amps, and it said it was way up there, 2 digits, like 40 some calories. And then I just converted, I said, I'm going to increase it 1,000 amps, 107,000 amps, and then my SKM software said, oh, you're down around point some calories. Not right. Can't, I mean, it's just not. It left the bad taste in my mouth. But in any case, I would always go back to the arcing current that you can calculate and then compare that, whatever's at 106,000 amps. And that, I think, will help you better, help you be more, feel better, sleep better when someone's dressed for those applications. Where fuses rated 1,200 amps are installed, you have to have that, so remember it's 1,200 amps. Indirect, and I mentioned a bunch of this already. Working space, barriers, right? You have working space requirements, we have barrier requirements in the NEC. All of those address likelihood of us accidentally coming in contact. Has nothing to do with severity whatsoever. So we have 110.26 spaces. We got to give our electrical workers space. 230.71, maximum number of disconnects. We changed the 6 disconnect rule because we recognized that when you have a panel board that has 6 disconnects in it, you can't barrier the line side of those service disconnects in them because it's one big copper or aluminum bus staring at you in the face, right? So we changed 230.71 to address, you can still do 6 disconnects, but you have to have barriers around the line sides. Service equipment enclosed or guarded, 230.62, that's your barrier requirements. And then the number of supplies, you could argue pulling more supplies to a facility. If I was going to pull 1 4,000 as opposed to 2 2,000s, right? My fault current is exactly the same. I have more of a likelihood of being in the faster clearing time for that overcurrent device because I've got a smaller overcurrent device. What's the time? I got 4 minutes. Okay, so let's talk. Questions, concerns, donations. Come on. Yes. That's okay. Yes. Yes. No, you're right. Okay, so, and you said the right word there, the AHJ, whatever makes the AHJ happy. If he says he wants the date changed, then you're gonna have to change the date. But you have to make a valid argument to say, look, this is one of my calculations. The fact that I put it in on a Monday as opposed to a Tuesday doesn't change the calories per centimeter squared, doesn't change anything because everything else is exactly the same. I would make that argument with my AHJ and have the discussion, but if the AHJ says, nope, I want Monday's date on it, then he's gonna get Monday's date on it. So there's nothing that you, I think your arguments are sound, but I mean, I have a lot of inspectors also say, this is what it says right here at the time of installation. So you might be labeling it that day. Yeah. Yeah, yep. But it does present a challenge. I mean, and like I say, a lot of the language, I mean, you got to remember, this is adopted into state law, right? And so you become a lawyer, so to speak, on a lot of the language, and you're following it by the letter of the law. So it can make it very challenging. The intent is to make sure that when you applied that label, that changes didn't occur between the time you did your calculation and when it was installed. That's the intent. Now, how we'll sometimes navigate those waters. If you go to NFPA, okay, you know that little statement of teaching somebody how to fish? We're going to go to www.nfpa.org/70. If you go to NFPA's website for the National Electrical Code, and you scroll down, now you can change the edition. So if you go to, say it was the 2020 code, and you say select and then you scroll down, I think it's done, and you'll look at there's errata, first draft report and second draft report. If you go to the first draft or second draft report, you've got to create, what did it do? It didn't show up? Huh. P? Oh, duplicate. Oh, wow, good job. See, who did that? Who said that? You know what you get? Here you go. I'll give you a fuse. Here you go. Here you go. Okay, so you go here, and what I'm going to show you is, now it's free to log in. You can, my password is incorrect. Yeah. Oop. Opa, opa. I do have a Windows short. Now it's going to let me in. So you go to what's called Terra View, not Terror. Terra View. Then you can go to, say, chapter 110, and then say 110.16. Bam! And then you come down to this. You show public comments. They didn't make a change in the second draft, but I'll show you basically what you can get to. But you can get to the change. So this is the suggested language. And then you'll see the statement of the problem. And this was the independent guys. And then it was rejected. And then you have the resolution. So if it was a first revision or a second revision, you can see what the panel said in the statement. Now, sometimes you're lucky because how you're arguing, you can go, look, here's the panel statement. This is what their intent was. And use that in your debate or discussion with an AHJ. Remember, the AHJ is not against you. The AHJ is trying to keep everybody on the same playing field, and they got to cover their butts. And if you can make your arguments and they're valid, then they put that in their report. And it's not you saying it, it's someone else saying it. Like we use IEEE documents and standards as our references. We don't want to be on stand trying to defend ourselves and say this is Tom Dimitrovich's way to do it. You want to make sure that you're referencing an industry practice or standard. Sure thing. Anything else? Yes?
Errant question. Obviously, have more knowledge.
I don't know.
Okay. Service entrance.
Yes.
Making the choice. Breaker. Fuse.
Yep.
Which is safest between generic work?
It depends, because if your fault currents are very high, right? Fuses are great when there's a lot of fault current. They're really good in that regard. Circuit breakers take a little bit more maintenance, right? So I would say, I would argue, what's the fault current? If I have very high fault current, I personally, in my opinion, I like the fuse technology just because it's simple. It's all straight rated, 200,000 amp interrupting rating, 600 volt rated, and it makes life a lot easier. Selective coordination is 2-to-1 ratio, right? So circuit breakers are a little bit more complicated, but both technologies can get the job done. If I do a circuit breaker, I would want to put a technology there that does arc reduction technologies and things like that, and sometimes even more so with a fuse, because it just depends on the available fault currents. But both are very good technologies to apply. Yep. Barcode. Oh, crap. Boy, you got, hold on, barcode. Woof, woof.
And tickets.
And tickets. There you go. Whoop. Did it come up? All right, there's your barcode. Oh, tickets. Jeez, oh man, did I go over? Tickets. You didn't do your job, buddy. Tickets, tickets, tickets. If you want, get your tickets here. Get your tickets.
Thank you.
There you go. Thank you. Thanks for staying in there with me. I know it's,
Thank you, sir.
it's your thing. Thank you.
RBS for ENF.
I feel like I'm in Vegas. There you go. Sure thing. There we go. You're welcome. Thank you. Thanks for coming. Try the veal. Thank you.
Thank you very much.
Thank you.
Thank you, sir.
Thank you, sir. Get your tickets here. Everyone's a winner. Remember, oh, okay, you could sell your ticket. Remember, if you win, I get half.
You work for you.
Yes, I do.
Can I get your card?
I can give you, you know what, give me your email. I'll send you my email. I don't have my cards with me. I'm terrible with cards. I can send you a link. If it's
How about if you, my email is paul.lucy@williams.com.
paul.lucy@williams.com.
Brzezowski, anyway,
Oh, Brzezowski, yeah. So I'm going to be here all this afternoon.
I'll catch you later.
Paul,
And I'll send you an email.
perfect.
I'm just going to my computer, but there's
Yeah.
all kind of issues I have with this. Because when I go to primarily
Yeah,
they give you a
No.
guess.
that's exactly right. Now, we have an IEEE.
You don't have any idea what you're going to get at any time during the day.
We have an IEEE paper that was written by our services division that tells you to use 50% of whatever they give you. And I know it's a kind of it might be a low number, but they did the paper based upon a bunch of examples. And I can send you
I got
that
another
paper.
problem with SKM. We're using a pad mount transformer. We had a guy come up with 90 cows. I got the IEEE paper on the test because the gap's so big. You can't get, it's poor.
Yeah,
So,
yeah.
so then I had a
Yeah.
guy say, well, interpolate. No, it only goes to 3 inches.
That's
and then
right.
they did the test where they put the channel locks in there. I'm trying to say, we got to fix our code. I got
Yeah.
people that won't open the door because it's got 100 cows on it. It's really less than 4.
Yeah, yeah.
Why IEEE post contradictive stuff is,
Yeah.
I mean, it
I know.
makes my life miserable.
I'm with you. I'm with
But I
you.
have to support every tier 2 in our company. From
Yeah,
New York
yeah,
to
yeah,
Houston
yeah.
to Washington State.
Yeah.
And the same questions come.
That makes it tough. It sure does. Yeah, but if we
I do
stay
wanna get you
connected,
because, and I really want to pin you down on less than 250 votes because